guys, I wanted to give you guys a little video that would show you how to collect your data for your lab tonight. Usually, of course, we would be in the lab and you get to do this yourselves, but in lieu of that, I'm going to do it for you and give you the data. So you need to be paying attention because I'm going to show you guys the measurements, and it's going to be up to you to infer what that means and to copy it into your data table. So tonight's lab has to do with the expansion of the universe. Edwin Hubble, right here in Southern California, in the mountains of Pasadena, nearly a century ago, he looked through a telescope and he saw something that looked really, really fuzzy. We'd previously learned about the Messier objects and how Messier had been looking for comets, and all of his numbers correlated with objects that were not comets, and we now know he put together this amazing catalog of objects in the universe. Well, Hubble was looking for things just like the Messier objects. He was looking for something called fuzzy nebulae, and he spotted something in M33, which we now know as the Andromeda Galaxy. But at the time, he just calls it a fuzzy nebulae. But what he came to realize is that that was actually a nearby galaxy, our closest galaxy. And he was able to measure the redshift of that galaxy. And the redshift is the light equivalent to the Doppler effect. So remember that the Doppler effect is just like hearing a train passing or a siren, and we hear a decrease in pitch. So with sound, we hear a decrease in pitch. With light, we see a redshift towards longer wavelengths of light to indicate a decrease in energy. What he noticed when he looked at that fuzzy nebulae that we now know to be the Andromeda Galaxy is that it was redshifted. And then he spotted these other fuzzy nebulae and he noticed the same thing. And what he concluded is that they were all receding not just from us, but from each other. Because everywhere he looked in the sky, as his calculations and his instrumentation became more detailed, he was able to see that galaxies were redshifted everywhere. So tonight's lab, we are going to be using a balloon to simulate the galaxy. And we're going to put little mock galaxies on this balloon and measure their distances from each other, and see if you can put together what the analogy is between the balloon and these measurements and what it was that Hubble found when he looked through his telescope. So in order to simulate this, I needed to have an assistant. This is Anders, and he is going to help me to place all of the galaxies on my universe. Sorry, I had a hole in the other one, so I had to change it. So I want to grab them and place them on. So you can see that all of these have a number, and then they have lots of dots. So now that we have all of our galaxies placed on our universe, the next thing we need to do is measure the distance. And Edwin Hubble was able to do this by measuring the rate at which he saw objects within that fuzzy nebulae in Andromeda receding. He calculated the distance by using things called standard candles. In his case, that standard candle that has a standard variation of brightness was a type 1a supernova, which we'd previously learned about. Those always go off at the exact same mass, which gives them the same luminosity every single time. And since he knew that luminosity, he was able to calculate the distance that supernovas that were within those host galaxies were away. So in our case, what we are going to do is we have to have a starting point. So the starting point we are going to pick is going to be galaxy number 1. So we're going to measure the distance between all of the galaxies starting at number 1. So my lovely assistant, we're going to start at galaxy number 1. So put it right on the number 1 to number 2. Okay, so hold your finger there. Sorry, I did not have string. And then we're going to line it up here, and you guys are going to have to look at the measurements in order to read it. So go ahead and line it up. So this is measurement 1. Leave it there. Perfect. Measurement 2, which is right there. Galaxy 1, doesn't matter where you start it. Just hold your finger. To galaxy 3. Be sure you're being very precise. Right where his thumbnail is where you measure 2, which means you're probably not going to have whole numbers. You will probably have decimals. Okay, number 1, 2, let's see, we're going to 4. 4 is right there. So 1 to 4. there. To 5. It was either this thing or an extension cord.
Wait, we didn't do 5.
We just did 5. Okay. Try and get from number to number, so like smack in the middle to smack in the middle. And that is to 6. So now my universe has expanded. I've added some air. But one of the things you want to note is, how did the galaxies change as the universe expanded? So go ahead, take a look. Ready? One common misconception is that due to the expansion of the universe, that galaxies expand too. And hopefully you can see that by looking at this model and by looking at the shape of the galaxies themselves, and again, ignore the model deficiencies here with the tape, but just looking at the galaxies themselves, hopefully you can see that that misconception is wrong, that the galaxies themselves are not expanding. Can you figure out what it is that's actually expanding? Hopefully, after you've gone through all of this, you can see that it's actually the space between galaxies that's expanding. It's not the galaxies themselves. If that were the case, the size of the Milky Way would be consistently changing, but we know that it's not. So galaxies are really stable, gravitationally stable bodies. So now we're going to repeat the same thing again, but notice we have a new diameter. So we're going to go through all of the same measurements again, starting from 1 and going outwards to 6. So number 1, right here, 1 to 2. So make sure you're measuring from center of 1 to center of the other. 1 to 2. 1 to 3. 4. 5. 1 to 6. 'So in this lab, you were mimicking the data that Edwin Hubble collected. We now know that the plot of his data of distance versus time is what we call the Hubble constant. And this is denoted, and you'll see in your lab, that this is denoted as Hubble with or H with a 0, or H naught is how we call that, with a subscript of 0. So in your lab, you will also be putting together a best fit line comparing this data. So after you have plotted all of your distances from galaxy 1, the next thing is to calculate the difference, and we call that a delta. So delta just means the change. So you're looking at the overall change in distance. We use Greek lettering, and a lot of times the Greek lettering was based off of landforms that they saw. In this case, this was after the Nile River Delta, so delta meaning change. So anytime you see that symbol, that's what that means. So in the lab, you're going to be plotting all of your changes and trying to put together a best fit line. And using the slope of that line, that was how Hubble calculated the age of the universe, which is pretty amazing. In your lab, you guys are going to be calculating the velocity, or the rate of recession of all of your galaxies. And the way that you'd calculate velocity is by using the equation v equals d over t, where v is velocity, d is distance, and t is time, second. And obviously that would have been millions of kilometers. But what I do want you to do is since we're using an analogy between our balloon and our freight galaxies here, is I want you to use an analogy comparing the centimeters of change to megaparsecs, because remember, in space we're not talking about centimeters, millimeters, or even kilometers. We're talking about vast distances. So you're just going to make a 1-to-1 ratio of your centimeters to your megaparsecs. So I hope you enjoyed this virtual lab, and have a wonderful day.